If we were in a physical classroom together, I would walk into class with some luscious and juicy type of citrus fruit. I'm a fan of a good blood orange or tangerine or clementines. I like the citrus fruits. But I would start to open up my juicy citrus fruit and I would ask students to raise their hand when they finally smell the juicy fruit. What I've done by opening up my citrus fruit is that I've created a concentration gradient. The scent molecules released from my tangerine or blood orange are very concentrated around me. And without any help, those molecules will move from where I am, an area of high concentration, to the outer reaches of the classroom, which are the areas of low concentration. It's these two areas with a difference in concentration that are a concentration gradient. All concentration gradients want to become homogeneously mixed. When you die, you will decompose, and the molecules that make you will become homogeneously mixed with this earth and this universe. So your molecules will move from where they are in high concentration in your body to areas where they are in low concentration, which is at the outer edges of the universe. I think on a big scale sometimes. Go big or go home. What's more important to us than a luscious, juicy tangerine or clementine is the verb diffusion. A concentration gradient, a noun, is two areas with a difference in concentration. But diffusion, the verb, is the movement that happens as those citrus molecules move from an area of high to an area of low concentration. If I were to put a drop of ink into a glass of water and come back an hour later, there would be a homogeneous mixture. I made this slide in like 2007. You like that? I did a pretty good job there, right? There's no energy required to make these molecules move from the area of high to the area of low concentration. Diffusion is a passive movement requiring no energy because it's the will of the universe to make a homogeneous mixture. And it's the will of the universe to create homogeneous mixtures from all gradients. And it is this rule that your body uses to move molecules. Simple diffusion is the movement from an area of high to an area of low concentration. It's a very stripped down definition. So this term would fit the example of my juicy tangerine. When we think about the cells in our body, though, simple diffusion is applied to molecules that are capable of fitting right in between the phospholipids of a phospholipid bilayer. Only very small molecules can do this. And because the tails of the phospholipids create that non-polar area that polar molecules are not capable of crossing, only non-polar small molecules can make the journey. Small non-polar molecules like oxygen and carbon dioxide are capable of making the journey by way of simple diffusion. In fact, if I were to stand here with my mouth open, I just did that. I just stood here with my mouth open. Oxygen would diffuse into me and carbon dioxide would diffuse out of me without any help. However, that rate of diffusion would not be fast enough to keep me alive. If I were, say, a jellyfish, I could just like jiggle around the ocean and the diffusion of gases would actually happen at a rate great enough for me to live. And that would happen without the use of lungs or even gills. Figuring out where a molecule is in high concentration and where a molecule is in low concentration can help you figure out the direction of simple diffusion. But there are other things that affect this process of simple diffusion. Going back to the example of the ink drop in a glass of water, there are two things that I could do to speed up that process that makes a homogeneous mixture. I could stir the water, adding kinetic energy to the system and increasing the rate of diffusion. I could heat the water, adding kinetic energy to the system and creating and increasing the rate of diffusion. So how quickly molecules move down a gradient and create a homogeneous mixture can also be called this time to equilibrium. This time frame is how long it takes a solution to make a homogeneous mixture. And it depends on the temperature and the other things that you see here. If I were in a larger classroom, it would take longer for the student in the very back corner to smell my tangerine. So distance matters. This time frame depends on the size of a molecule too. Smaller molecules move a lot faster than big ones. This time frame also depends on temperature. And as we know from the example of heating our glass of water with the ink droplet, increasing temperature decreases the time to equilibrium. We get there faster. There's also something called the steepness of the gradient. And this is the relative difference between the area of high and area of low concentration. If the concentrations are very, very different, it will take a long time for the molecules to move and make a homogeneous mixture. But if the concentrations are relatively similar, it's not going to take a very long time until we create that homogeneous mixture. The last thing that affects the time it takes to get to a gradient to get to a homogeneous mixture is electrical forces, voltage, distribution of charges, electricity. I just want you to keep this in mind because when we hit a chapter about muscles, voltage is really going to come into play.